Hi, my name is Monia Hussein from Section C. This is my Lab 1 video about constant velocity motion. Objective of this video is to compare the observed positions of an object in constant velocity to a GlowScript model of the object's predicted positions. The object in motion is the GT foam ball. The video of the ball was put in Tracker to gather time and position points, as you can see here. Then I use those data points in my GlowScript code, as you can see here. Then we get this model when we run the code. For this lab, we use the fundamental physics principles, Newton's first and second laws. The first law states that an object in motion will stay in motion unless acted upon by another force. Newton's second law states that the force acting upon an object is the product of mass and acceleration, F equal ma. If the foam ball is in a constant velocity, that means no force should be acting upon the ball. And with no force, there will be no acceleration. And this is the momentum principle. With this, we can get the velocity update formula and a position update formula. And this is how to derive the formulas. These are my calculations for the code. So I gathered the first 2 points in the tracker data graph, as you can see here. Using these 2 points, we can then get the ball's initial position and then the ball's initial velocity. Even though this is the average velocity, given that the time is very small, it will work for our initial velocity. Here our observation time is 0 seconds and the time of our last observation. Here is my GlowScript code. Here I have the ball's mass in kgs, the initial position, initial velocity, initial time, change in time, the last observed time, the net force is set to 0, and this is the formulas. When we run this program, we get this model, the graph, and the data points that we will put in an Excel sheet to compare with the experimental data points. We use Tracker to do a frame-by-frame analysis of the foam ball. As we play the video, the frame number and position points update. Here's the number of frames. The dots represent the new position of the ball after each frame. And then this is the graph that has been used with these data points. Using these data points, we can go to an Excel sheet and compare the model's data points and the experimental data points, which then gives us this graph. Here you can see that they started the same in the same origin, but the experimental data is higher than the model data. And this could be for my mistakes in Tracker, probably from plotting points in each frame, and it could be the surroundings. We are assuming that there is no net force, but any thing could factor from the surroundings. So what if our results were flipped? So here, this is the original graph. If we were to flip this in the y-axis, then it would be going the other direction. It will be negative data points, and it will show that it's going to the left. Similarly, if we flipped it in the x-axis, it will be negative, possibly going in a different direction. To answer this what does it mean question, I will say no, because every everything exerts a gravitational pull on each other, no matter the distance and strength of the force. So we cannot accurately calculate the number of pushes and pulls unless there's some special lab to make the net force truly zero. And since this is just a regular lab, we can only assume the net force is zero, but there are so many things affecting the force. Thank you for watching.